Hi, my name is Mark. My colleague Lorenz and I both work at Cloudflare, working on the Unimog layer 4 load balancer on our edge. Today, I'll be talking to you about bad middle boxes, specifically ones that violate the assertions in RFC6437. Now, violations of RFC6437 doesn't really have any meaning to it, but in order to explain it, I have to first explain IPv6 flow labels. IPv6 flow labels are a 20-bit field in the IPv6 headers that are meant to contain a client-side value that is consistent for every packet of a connection generated by the client. This field can be used as an alternative to layer 4 headers, such as ports, in hashing algorithms used in load balancers. And the reason that this would be helpful is that on IPv6, finding the layer 4 header and therefore the port fields can be a little bit tricky. And coincidentally, me and Lorenz both work on the load balancer at Cloudflare, and that's also written in evpf XTP. So being able to see if we can use flow labels instead of ports for IPv6 is quite important. But can we actually use flow labels? Well, there's a blog post from APNIC that says we probably can't. It says that it's probably not a good idea to use it as an input for flow hashing because there are apparently middle boxes on the internet that interfere with this flow label. They suggest that flow label contents between a SYN packet and a subsequent ACK packet that's sent by a client may actually differ. And they surmise that it's probably CPE, so customer routers and equipment, or other middle boxes on the internet that are actually altering this field. But there's not a lot of evidence or numbers in the blog post, so it will be great for us to find out for ourselves if that's really true and how much it occurs on the internet. But how can we actually find this out? Well, enter evpf. We can use evpf to determine whether this occurs on our edge. Using the Cilium Cloudflare co-maintained library that's written for Golang, we can do this. The library has bpf2go, which is a code generator that allows you to have a bpf.c file, and it generates all the bindings for Golang. It has supports for loading and attaching kprobes and support for bpf compile ones run everywhere. Using this library, we will write a bpf kprobe specifically meant for one of the TCP functions in the kernel and load it and attach it. And using perf events, we can actually get that data out from the kernel and into user space so that we can do something with it. But how do we actually make sure that we can see the SYN packet and then the ACK packet and see if the flow labels have changed or not? Well, what we need to do is find a way to record that SYN packet. And the easiest way of doing that is actually a socket option on Linux, where you can instruct the kernel to save the SYN packet for every connection made. Now, this is enabled by default, and enabling it for all our sockets on our edge is a little bit tricky. So here comes the pidfd getfd syscall, where we can actually get the kernel, once we give it a process ID, to enumerate all the file descriptors of that process. And once we have all of those, figure out which ones are TCP ones and which ones are listening sockets, and then actually set the socket option on that socket so that the kernel from that point forwards will save the SYN packet for every established connection. Using this, we can then have our kprobe compare the values, and if the values differ between the flow label in a SYN packet and the flow label in an ACK packet, we can actually generate a report and send that over the perf event buffer into user space and do something with it in user space. And what does that result in? Well, a single Golang compiled binary that's static. It can run mostly anywhere. We don't need to ship any kind of tool chains to our edge machines. You simply give the program a process ID and it finds a TCP socket, sets the socket options, loads the kprobe and attaches it. And if there is indeed middle boxes interfering with packets, we will receive data from the kernel into user space and are able to do something with that. So what we'll do is we have the code that is a proof of concept on GitHub. We'll try and deploy a variant of this code on our edge and come up with some good findings. And once we do have that, we'll try and write up a blog post and share that with everyone. Thanks for listening.